So now we're going to get to talking about Maxwell's equations. If you remember, we had started off talking about a long time ago, way before the break, we talked about how the electric flux can be regarded as the integral over the surface E dot dA, and that by by Carl Gauss's law was an enclosed charge over epsilon naught. Okay, and analogously, we didn't really mention it, but there's a magnetic flux. I mean, we barely mentioned this, and that's integral B dot dA, and that turns out to be equal to 0. Now, integral B dot dA is equal to 0 because there are no magnetic monopoles. There's only magnetic dipoles. There's north and south always. You have a magnetic moment. Magnetism comes from loops, comes from electricity. It always has polarity. You've got a north and south magnetic end, and so that means that the flux is going to be 0. There are no magnetic monopoles. Now, in theory, turns out that there is the possibility in a couple of models of the Big Bang to permit the existence of a few magnetic monopoles in the universe, but by and large, there are just a few in the universe, and you're not likely to actually encounter one. Okay, so so we got these two relationships right here. Gauss's law. We also introduced the idea of Faraday's law. And Faraday's law was that the EMF, now the EMF we also know is the integral of E dot ds, so the integral E dot ds, and so around a closed loop or something, that would be equal to the minus the rate of change of magnetic flux in that loop. And so so we have there Faraday's law of induction, and then we have Amperes law. And so we did a similar sort of thing here, Amperes law, integrate around loop B dot ds, because this turned out to be very, very useful for us for Faraday's law. And so Amperes law, integral B dot ds, and that turns out to be equal to mu naught, rather that turns out to be equal to mu naught I. Okay, so there we had this. Okay, and so we look at this and we say, okay, so we got Ampere's law right here. And so these equations right here became very interesting to a Scottish physicist by the name of James Clerk Maxwell. Okay, so Maxwell living in the 1800s. And in particular, he was looking at Ampere's law, and that was the integral B dot ds, and that was equal to mu naught I. And he compared that to the integral of E dot ds, and the integral of E dot ds we had already realized was equal to the rate of change, negative the rate of change of the electric flux. And so as he looks at this, he begins to realize that there's something that's just not quite right. Because one of these, because the other was pretty symmetric, so here we have this integral here is related to the change of the flux. This one's actually related to rate of change of charge. So he starts thinking about this. And he thinks about it and said, well, let's consider a situation. So let's consider that we have a long wire and we have a capacitor and a long wire. And so we have current flowing in this wire and along like this. So we're charging up a capacitor. So clearly, as the current is flowing to charge the capacitor, then it creates a magnetic field. Right-hand rule. So magnetic field out of the board here, into the board there. Out of the board there, into the board there. But he started thinking about it and said, well, there's a problem because we got magnetic field, magnetic field, magnetic field, magnetic field, all over here. But what about right here just beside the capacitor? Does it make sense there's no magnetic field there? Because after all, if this gap is very, very small, this bit of current produces magnetic field around it. This bit of current charging it makes a magnetic field. This little bit, but literally, if you were to imagine drawing an Amperian loop right there, you would have no current flowing in it. So you would have mu naught I would be 0. That would suggest the magnetic field is 0, but clearly the magnetic field there can't be 0. And so since the magnetic field there cannot be 0, then this led him to decide there's got to be something else going on right there. And so what else could possibly be happening there? And so he thinks about it and thinks about it and says, well, it's as if there's like an imaginary current going through there. And so that imaginary current we call the displacement current. So the displacement current, we're charging our capacitor right here. So we're charging the capacitor. We got current here. We got current here. We imagine there's some I sub d displacement current going through. Now the displacement current is not really current. It is the displacement current is going to be equal to the current that's flowing in and out of the capacitor. But it's not really current. It is equal in units, but it's not the same thing because the actual current is in fact rate of change of charge. What's displacement current? Well, it's not charge. There's actually no charge flowing inside the capacitor. Remember, the charge is flowing into one end of it here, accumulating those plates, flowing off of that end, leaving those plates. So there's not really anything in there. And he says, well, what is happening in there? Well, he says, well, there is actually electric field in there. And the electric field that's in there is related to the current. So the rate of change of the field, because remember, the electric field in a capacitor, is going to be related to the charge on the capacitor. The voltage in there is related to the charge of the capacitor. So he would say, therefore, the displacement current has to be related to the rate of change of the field. Well, the field in there is also means, that we've got a flux. So we think about it, and we say, well, wait, let's think about it. Okay. And so the charge on the plates, what's the charge on the plate going to be? Well, we know that sigma, that's going to be Q over A, okay, that is going to be related to the electric field, okay. So the Q over A, that's equal to the electric field, or rather sigma over epsilon is the electric field. So the electric field, sigma over epsilon naught, okay, and so that means that Q over A, which is sigma, is going to be equal to epsilon naught E. Okay, well, if we multiply that out, then that would mean that sigma is going to be epsilon naught A times E. Okay. Or rather Q. Q over A is that. So Q equals epsilon naught A times E. Well, you would take a derivative. So we have Q equals epsilon naught A E. So the current is dQ dt. So that's going to be epsilon naught times the derivative of AE. Well, that's the electric flux. So this is epsilon naught electric flux. And so the displacement current is equal to that current. So it's going to be equal to epsilon naught, derivative. Epsilon naught derivative of the electric flux. Well, let's go back to Amperes Law. Amperes Law, integral B dot ds equals mu naught I. Well, what if there's no I? Okay, because that means, integral B dot ds, you do that out here, you're perfectly fine because you have an I. What if you do it around here? Well, there's no I, so Maxwell would say that in this area right here, then you would do mu naught displacement current. So it's acting as if there's current in there. It's really what happens is the displacement current is epsilon naught. So this is going to be mu naught I plus mu naught epsilon naught rate of change of the electric flux. So now this relationship B dot ds equals mu naught I plus mu naught epsilon naught rate of change of the electric flux. Now, let's compare that. For Faraday's law, integral E dot ds equals negative rate of change of magnetic flux. Now we're saying, or what happens is Maxwell says integral B dot ds equals minus mu naught, or equals mu naught I plus mu naught epsilon naught rate of change of electric flux. Now, if you look at these two equations, we actually now call this the Maxwell-Ampere law. Then if you look at those equations right there, then what that tells you is that there's now a symmetry here. Rate of change of flux here creates this electric field. Rate of change flux here creates a magnetic field. Moving electric charges also makes a magnetic field. Moving magnetic charges, well, there are no moving magnetic monopoles, so there is no other term to create a field there. So now we have the full-blown rendition of Maxwell's equations. We have that the integral of E dot dA equals enclosed charge over epsilon naught. Integral B dot dA equals 0. Integral of E dot ds is equal to minus rate of change of magnetic flux, and integral B dot ds equals, now we can write this, we can change the order here, it's equal to mu naught epsilon naught rate of change of electric flux plus mu naught I. And that gives us Maxwell's equations. So, even though Maxwell didn't come up with any of them, he did at least add this one term into the equation for Amperes law, and that made Amperes law and Faraday's law symmetric laws in terms of how they treat fluxes. And then what he does is he does some calculus, which really makes him absolutely famous. But up to this point, all he's done is add this one term in to Faraday's, to Amperes law rather. But these are what we call Maxwell's equations.